So recall that any number is congruent to its remainder modulo m. So what we can do if we are talking about congruences modulo m, if we are looking for remainders modulo m, we can just represent any number by its remainder. And also recall that we have shown that arithmetic operations, addition and multiplication, preserve congruence. So if we would like to apply arithmetic operations to some numbers, and we would like to do it modulo some m, then we can apply them with operations to numbers that are congruent to the original numbers. So, for example, instead of applying operations to original numbers, we can apply them directly to remainders of the original numbers. And the remainder of the result of the operation depends only on the remainders of the original numbers to which we apply our operations. So what we can do, we can create tables for arithmetic operations for remainders over some module. And let's do it, for example, for module for m equal to 7. And here is addition table. So rows are labeled by one of the summands, columns are labeled by the other summand, and in the cell on the intersection of a row and the column, we write the remainder of the result of addition. For example, if we consider the sum of 4 and 1, then we look at the row labeled by 4, look at the column labeled by 1, and in the intersection we have 5. So 5 is the remainder of the result if we add 4 and 1, and this is easy to see. And let's consider one more example. For example, let's consider 6 plus 6. So then we have to look at bottom right corner of this table, and here we have 5, and indeed if we add 6 and 6, it is 12, and modulo 7, it is congruent to 5. So 5 is the remainder of the result of addition of two numbers having remainders 6 modulo 7. So the remainder of the sum will be equal to 5. Note that this table has nice and simple structure. We can consider the same table for multiplication. Modulo 7. Again, we have a table. Rows of the table correspond to remainders modulo 7. Columns correspond to remainders modulo 7 again. And in the cell, we write the remainder, which corresponds to the product of the number in the row and in the column. Again, let's consider a couple of examples. For example, if we consider the product of 4 and 3, then it is 12, and the remainder modulo 7 is 5. So this is what we have in our table. And for example, let's consider again, let's consider now product 6 of 6 and 6. 6 by 6 is 36. Note that 35 is divisible by 7, so the remainder is 1, and this is what we have in bottom right corner of the table. So that's what we have. Now, note that using these tables we can perform modular computation. If we have some arithmetic expression with some numbers, we can substitute all numbers in the arithmetic expression by their remainders and apply operations according to the table. So each time we would like to apply an operation, we look at the table, just like with usual addition and multiplication table in school. We can just apply these operations one by one and do the computation. And also, these tables are convenient to observe properties of operations. And let's just try to do this. Let's just consider whether modular subtraction is possible. So what is modular subtraction? So let's consider the following question. Suppose we have two numbers, a and b. Is there such a number x such that a plus x is congruent to b modulo 7? Note that x will play a role of b minus a in our modular arithmetic. So is this always possible? And for this we can just look at this table, and we can observe that each row of this table contains all possible remainders. Okay, why is this good? Note that in this expression a plus x congruent to b, a plays the role of the row of this table, x plays the role of the column, and b plays the role of the value in the cell of the table. And the question is the following. So the question we are asking is, suppose we have some row of the table, and suppose we have some target value b. Is there a column such that in the intersection of our row and this column, we have our target value. And note that in each row we have all possible values, so whatever row we are given and whatever target value we have, in any case, there is some cell with this target value, and so there is some x which is equal to which satisfies this congruence, such that a plus x is congruent to b modulo 7. So this x exists for all a and b, and okay, what we can do now, we can consider this x given a and b, we can consider this x such that a plus x is congruent to b modulo 7, and note that the same argument holds for all modules m. So if you substitute 7 by any number m, still x exists. And x plays the role of modular subtraction. So it plays the role of b minus a in modular arithmetic. Note that the existence of x is natural. We can just pick b minus a as an integer and consider the corresponding remainder modulo 7. And the equation will be satisfied since congruence is preserved under addition. Okay, now let's consider modular division. Suppose we have two numbers, a and b, and now a should be non-zero. Is there such an x that a times x is congruent modulo times to b modulo 7? Okay, note that x corresponds to b divided by a in modular arithmetic. And note that a should be non-zero because, okay, if we multiply 0 by anything, it will be 0. So, of course, if a is 0, this is not always possible. But if a is non-zero, we can ask this question: is it true that x exists? And here we can look at multiplication table, and again we can see that that x always exists if a is non-zero. Again, each non-zero row, each row which is not the first one, contains all possible remainders. And again, a here corresponds to a row, b corresponds to the target value in this row, and x is a column. If we pick any row which is not the first one, then we can see all possible values in this row. So whatever target value, whatever b we have, there is a column having this value on the intersection with our row. So modular division is always possible. So given a that is not equal to 0 and b, we can always consider x such that a times x is congruent to b modulo 7. And we have shown that such an x exists, and again x plays the role of modular division. It is b divided by a in modular arithmetic. Note that x is still some integer number, it's some remainder modulo 7. It just plays the role of division in our modular arithmetic. So everything is finally good, it seems like that, and the construction of modular arithmetic is complete. We have addition, multiplication, subtraction, division. Is this right? It turns out that no, and for this let's just consider some other module. Instead of 7, let's just consider 6, and let's consider multiplication modulo 6. And here is the table. And observe that rows that correspond to numbers 2, 3, and 4, they do not contain all possible remainders. So there are some remainders which are not presented here. And in particular, if we pick a to be equal to 3, so if we pick row labeled by 3, and we pick value 1 in the right hand side, then there is no such x, there is no such column such that 3 times x is congruent to 1 modulo 6. So this is not always possible. So for modulo 7 we found that modular division is always possible, and for modulo 6 it turned out to be not the case. So what is going on? Why it happens that we have division modulo 7, but we do not have division modulo 6? What is the difference between 7 and 6? Why it works in one case and doesn't work in the other? And it turns out that the modular division is actually more complicated than it seemed before, after we considered modulo 7. And we will discuss we will discuss these differences, these complications in further in this course. We will see what is the difference between 7 and 6 that makes division impossible for modulo 6. Okay, let us discuss what we have in this, what we had in this course. We have started with some simple notions, divisibility and remainders. And then from them we developed more advanced things. We developed the basics of modular arithmetic. We have addition, multiplication, subtraction, modulo some number. But things are complicated and we do not understand them completely. So the division turned out to be complicated. Okay, is it bad that things are complicated? Is it bad for us in any sense? And in some sense, yes. We would like things to be more simple because we would like to use our number theory for computations. We would like to compute things effectively. And if something is complicated, it is harder for us to compute. But maybe in some sense complicated is good. And it turns out that yes, this is true. Complicated things are also important and they are crucial for cryptography. Cryptography relies on things that are hard to compute. So if we have something that is hard to compute, this is actually, in some other sense, this is good for us.